lugar, eu gostaria de agradecer à audiência por permanecer aqui até as últimas sessões do Congresso, apesar desse frio intenso e desse minuano que apavora os pagos. Para quem não sabe, minuano é o nome desse vento que canta e balança as janelas aqui do Sul, e o pago é a nossa terra, né? Eu também sou de Porto Alegre. E, em segundo lugar, thanks, Fabrizio, to come here and give all this talk for us. Este é a quarta palestra que o professor Fabrizio Ruggeri vai apresentar aqui para nós. Eu creio que a presença dele foi muito produtiva. E, bom, nessas alturas, né, no último dia de congresso, a quarta palestra dele, eu acho que quase todos já conhecem ele, não necessita muito detalhar a apresentação. De qualquer forma, se vocês querem mais detalhe a respeito do trabalho do professor Fabrizio, vocês podem olhar a homepage dele, que eu estou colocando aqui. Eu gostaria de salientar, entre as várias atividades que ele tem, atualmente, ele é chair do comitê científico que está organizando o próximo ISI Meeting em Marrocos. Ele foi presidente da International Society for Bayesian Analysis. Ele tem, aqui não aparece, mas mais abaixo, 4 livros publicados, editados, e um especial que é em análise bayesiana, Bayesian Robust Análise, robustez bayesiana, desculpe, que eu acho muito interessante, que é o assunto que a gente tem trabalhado em conjunto. E, bom, além de pesquisador no CNR de Milano, ele também é professor numa universidade na Austrália. E, enfim, aí vocês têm uma parte do currículo dele. Para mais detalhes, vocês olhem o currículo. Então, very welcome, Fabrizio. It's your turn now.
Okay, let's start the thanking part in an unconventional way. I would like to start thanking Deutsche Lufthansa, because when I was here giving all my talks, discussing with people, preparing slides and so on, closed in my hotel, in this hotel, my luggage has been traveling all over the world. They have no idea where it is. Hopefully, I will meet my luggage somewhere in the world, hopefully in Italy. And this is something also which is related to my talk today, because there is maybe an issue. Is Lufthansa reliable or not? Usually in Europe, we have this stereotype so that Italians are not reliable and Germans are. Of course, I have a different opinion on that. And it's quite biased, I would say. And so the issue is Lufthansa reliable or not? So this is an hypothesis testing. And then there are 2 agents which are competing on this. On one side, I am the guy who is the defender. On the other side, we have the other guy who is the attacker, who is the customer service at Lufthansa. So we are taking actions, making decisions, and that's what I'm going to talk about today in this very simple idea, but new one that I'm going to present to you. So every one of us is taking an action. For example, yesterday, the customer service of Lufthansa called me and told me, look, your luggage might have been put on the flight to Rio, but we don't know if it arrived, and we have no clue about where it is. So this was the action taken by Lufthansa. What was my reaction? My reaction was, why did you call me? Just to tell me there is nothing. So what was the influence on my opinion about reliability of Lufthansa? So this is a very simple problem. So that was the first thanks was, I said, to Lufthansa. I think Danny is not here around. Danny and Laura are not here because they had problems with Alitalia, but they are not allowed to say that. So I'm just talking badly about Lufthansa. Second thank goes to the scientific committee and the friends from ISBRA, the Bayesian session of ISBA, because they gave me the opportunity of presenting essentially everything I've been doing in my life. As Marcia said, I gave 4 talks, so I had the opportunity to present everything. At this point, there is nothing left for next invitation, so I'm wondering if someone is going to invite me, since I have nothing else to add. And this is really a pity, because I like a lot to come back to this country. I've been here many times, so I would like seriously to thank the people who invited me, the people with whom I've been staying here, discussing, all my friends. It's a great pleasure to be here. Now let's move to science. Also, the topic I'm going to present today is called adversarial hypothesis testing, and this goes inside a new area which is called adversarial risk analysis. I had the opportunity in these days here in Porto Alegre to present some work, some ideas I've been working on starting almost 30 years ago. I am quite old, by the way. 30 years ago, almost 30 years ago, I started working on elicitations of prior, consequences of elicitation in terms of Bayesian robustness. So that's something I spoke. Then I spoke about something I started working on 20 years ago, which is reliability, Poisson processes. Something else I started working 10 years ago, which is stochastic differential equation application to biology, engineering, and other. And what I'm going to talk today is something I started just a few months ago. All of this just to tell you that if you have tough questions about this topic, well, I still have to learn a lot about it. And the good guy, the guy who knows a lot, is the guy who introduced me to this topic, is my major co-author. So we have been writing 2 books, 20 papers together, is David Rios Insua from Madrid. So this is a joint work with David, a joint work with another good friend of mine, Refik Soyer, who is a Turkish guy in Washington, at George Washington University. And then we have also a young person who is doing all the dirty job, computation or something like that. Paul is around, so computation, something like that, with Jorge González Ortega. So this is what I'm going to talk about, adversarial hypothesis testing. So essentially, there will be a short introduction. David would have given a longer introduction, talking about relations with game theory, but as I told you, I'm still learning about this. So I will say something about adversarial risk analysis, but then I will go into introducing you this, I would say, simple idea, but I think it has great opportunities, great possibilities in terms of applications, and we are going to work on these serious applications in the near future. And I will give you also some illustrative examples. And then we have been working also on something else, which is somehow related to this idea, but I will not just a couple of slides in total, which is about acceptance sampling, which is something in industrial statistics, and robustness, which goes back to my interest and David's interest long time ago. So let's start making a very quick summary of what a decision analysis problem is, essentially a Bayesian decision analysis, because, by the way, all of us in this group are Bayesian, so we are taking a Bayesian approach. So we have a decision maker, which has to make a decision, of course. And the goal of the statistician, our goal is to help this person to make decision under uncertainty. So this person has some alternatives, actions. In my case, should I fly Lufthansa next time or should I fly Alitalia? That's a big problem. It's not clear to me what to do. But we have a set of actions, or called alternatives. On the other side, there is something which is unknown. The uncertainty is modeled through a parameter, theta, which is somehow related to the state of nature. And then there are some consequences. When the action A is taken by the decision maker and theta is the state of nature, that is affected by the state of nature, then there are some consequences which are C of A of theta. And then related to these consequences, there is some utility function or loss function. Decision analysts like to use utilities, statisticians prefer to use losses, but it's essentially the same. So what we are doing here is perform an experiment collect data, we have an observation X, and we use the usual Bayesian machinery to get the posterior distribution on the parameter theta. At this point, there is a very important principle, which is the subjective expected utility principle, and the idea is to find the actions which maximizes such the expected utility, so which is this quantity here. So this is the posterior distribution, so this is the posterior expected utility, and we try to find the action A which maximizes this one. As I said a few days ago when I was talking about Poisson process and reliability, the choice of the posterior mean in a Bayesian framework is motivated by decision analytic reasons. The Bayesian the posterior mean is the quantity which minimizes the posterior expected loss, that is, under a squared loss function. So there is a decision analytic explanation for the choice of the posterior mean as an estimator of the parameter of interest. So we are in this situation where there is just one agent which is playing against, let's say, nature. And the idea in adversarial risk analysis is quite different. There are more agents, more intelligent agents which are acting together and maybe fighting each other. And there is a defender, which we'll call she, and there is an attacker, we call he, this one, and both of them are expected utility maximizer. There could be more than two agents involved, but for simplicity, we're just considering two agents, defender and attacker, she and he. And there are many examples which are motivating such a choice. We have been working a long time ago with David Rios and our former student Jesus Palomo on auction bidding for projects in the oil company. So we were working with an Italian company leader in the world in terms of construction of oil plant, especially in the Arab world. And the idea here is that there are different companies from Italy, China, Japan, United States, somewhere else in Europe, which are bidding to get the plan to be built. And of course, there are issues which are related to the best action that each company has to take. For example, if the Italian company is bidding a lot, saying, we will get a lot, we want a lot of money to build this plant, it's very unlikely the Italian company will get it. Probably it will go to the Chinese company, which is asking for less money. So, but if the Italian company is asking for less money, then there are chances the Italian company is losing money if the plant is assigned to the Italian company. So there are two sorts of gains or losses. There is a gain if the Italian company get it and gain money, but there may be also a loss if they are asking for not much money. And the same is for terrorism. A lot of work related to adversarial risk analysis started looking at terrorism and counter-terrorism. Try to understand what the terrorists are doing and trying to find the best action that the good guys can take against this terrorist. And also there are competing interest groups. The example I made the other day here during the round table was about the Italian city of Taranto, which relies a lot on a steel factory. And there is a big debate also in tribunals involving also statisticians about keeping or not such a factory. Because on one side, that factory is creating environmental problems, but on the other side, that factory is giving job to most of the people in that city. What to do in this case? So there are two different issues, two different perspectives, which is not easy to understand what to do in this case. So you can see there are plenty of problems which are addressed by considering intelligent agents which are competing or fighting each other. So also the decision taken by one agent, of course, will affect the others. Because if the company in the steel factory is investing money to prevent pollution somehow, that will affect, of course, the behavior of the environmental group and others. So there is an issue which here is the area in which I should learn more. It's about game theory. In game theory, often it's supposed that the two agents are sharing the more or less a lot of priors, utilities, and so on. And there is also knowledge of what the other person is doing. Somehow the notion of Nash equilibrium is somehow related to this one. But the point is that this is quite unrealistic, because what do we know about the terrorist? What do we know about what the other companies bidding for the oil plant are planning to do? So we might have some guess on that, but not exact knowledge about what they do. So there is an action of, so the probabilities and the utilities which are owned of the attackers are unknown to the defender. And in this environment, in this framework, we are taking the position of the defender. So we are trying to help the defender to understand the probabilities and the utilities of the other attacker, and especially which action is the attacker is going to take if the defender is taking some other decision. So the influence between the two of them. So the idea is to mitigate the effects of the actions of the attacker and saving, protecting somehow the defender. So if you want to know more about adversarial risk analysis, which is a sort of framework to manage risk, so this word risk will appear only once here in my slides, but or part in the title adversarial risk analysis, but I should talk a lot about risk. So all of this is, the work we are doing is mostly motivated by risk in different parts of our life. Already mentioned some cases. So it's a framework to manage risk derived from actions of intelligent adversaries. David Banks and Jesus Rios Aliaga just published last year a book, Adversarial Risk Analysis, and also they are authors and co-authors of 3 important papers in the area. So you can see them. They are one in the JASA. This is I would say the very first paper on this is an interesting one. It has also relation with game theory. It's an interesting paper in JASA, and also they wrote a couple of papers in risk analysis. This is about counterterrorism, this modeling opponents in adversarial risk analysis. So there are many other papers, because this, as I said, is an area which started very recently and is growing a lot. So what I'm going to present, as I said today, is adversarial hypothesis testing using concepts from adversarial risk analysis. So there are some hypotheses, and the defender, the agent, defender, has to choose which one is the right one within brackets, within quotes, but just by using some data coming from a source. But there is the problem. There is also the attacker. And what is the role of the attacker in this case? Well, the attacker is modifying the data which are coming from this source, because the attacker wants the defender to make the wrong decision. And to make the wrong decision, the attacker is changing the data coming from the source. As I said, and the attacker is getting some benefit out of this. So we are studying this problem from the point of view of the defender perspective, and the idea is that of forecasting the decision of the attacker. And that is possible only through simulation. And we will see in which way we will do this simulation. So trying to simulate the decision-making problem of the attacker. So the defender will think as if she were the attacker, and you will see how it works. So an example, a very simple example, is related to emails. So we could suppose that the defender is receiving a batch of emails, and she has to decide if they have spam inside or not in this batch of messages. And the defender has her opinions about the flow of legit, so right messages, or spam messages. The point is that there is this attacker which is in some way, and we will see different strategies, is in some way changing the flow of these messages, try to confound the defender against some benefit. So there are some rewards or gains or losses for both the attacker and the defender, depending if the batch is accepted or not by the defender, and if the batch includes just legit messages or not. And just to make, just to express more formally the problem. So we suppose we have just two simple hypotheses. As you can say, this is really, as I said, just the idea based on very, very simple, the simplest cases as possible. So we have two hypotheses to choose from, theta naught or theta 1. Then there is an observation x, which is generated from some model, according to some model, which depends on a parameter theta. For example, an exponential with parameter theta. The point is, which theta? Theta 1 or theta naught? That is the point. And this observation x generated by this model is, according to this model, is changed, modified by the attackers, which is taking an action A. We will see which kind of action A is possible to take. At this point, this x has been modified into y by the attacker. So the defender is observing y, not x. So, and the defender has to take her decision based on y without knowing x, of course. So depending on the decision D and the actual value of the parameter theta, then there are some losses or utilities for both agents. So the A is somehow try to minimizing his losses or maximizing his utilities, but on the other side, we are working to minimize the losses of the defender. And that is what we are going to do. In our paper that is almost done, and I would like to get also feedback because we are going to submit the paper pretty soon, so if we can make changes, it will be great. Before the referees see it, it will be great. So in our paper, we have also influence diagrams. David is very fond of them, so this is a tribute to David. Influence diagrams. They are directed acyclic graph with three kinds of nodes. You will see one here. You will see square, hexagon, and circles. So square are decision node. Circle are random nodes, and hexagon are value nodes, for example, utilities and loss. And then there are arrows. So when an arrow goes into a value or an uncertainty node, they indicate respectively functional or probabilistic dependence. So the utility function at the value node depends on its preceding nodes, and the probabilities of the chance node are conditional on the values of the x-direct predecessors. When there is an arrow into a decision node, then it means that when the decision is made, the values of the preceding nodes are known. So this is, in our case, is called a by-agent, because there are two agents, influence diagram. So here we have the decision made by the defender, the decision made by the attacker. Also, you can see the color, because when there is white is defender's part, when it's gray is attacker part, when it's mixed is something which is affecting and interesting both of them. So here we have also something which is random. The parameter theta is random. The x that we are observing as a consequence of theta is random. The y that we are observing, which is given to the defender, is random. This depends on x, but depends also on the action of A. And the decision of the defender depends on y. And related to the decision, there is a loss function for the defender, but also the loss function of the attacker is not just a decision by him. It's somehow influenced by the decision of the defender, and we will try to see how to cope with this later on. So now we start splitting the problem in two parts. First, we are looking at the point of view of the defender. Then the defender is looking at the attacker's point of view, and then it goes back to the defender. We could keep going back and forth this way, but since I have only 1 hour, even less, we will stop at some point, which is, I would say, almost immediately. So because the defender may decide something which will affect the attacker, which will decide something will affect the defender, which will decide something will affect the attacker, and so on, and so on, so on. But we will stop defender, attacker, back to defender. That's all. Just because we have to stop at some point. Okay, so now, what is the difference before? From the point of view of the defender, the decision of the attacker is random. because the defender does not know which actions the attacker is going to take. I know that I'm quite boring, but as I already said to Elio, that I'm making him a great favor, because I will be so boring that everyone will appreciate even more Elio's talk, which is after my own, okay? So, Elio, you gave me a beer, okay? Okay, good. Belief. I asked beer, not wine, because we are in Brazil, beer, or cachaça. Oh, so, a defender D. So we are taking the position of a defender D. So the defender has beliefs on the hypothesis, very simple one. Look, when I put a D, it's defender. When I put an A, it's the attacker. It's easy. So we have two hypotheses, obvious how to give the probability, two probabilities. Then the defender is also considering a model from which the data are coming. For example, it might be an exponential. So this is his model, R model, sorry, depending on the parameter theta. Then the defender has also an opinion about the Y she will get if X was the true value, the real value, the actual value, and A was the action by the attacker. So this is a belief on how the action A by attacker modifies the actual X into the observed Y. Then there is, this is the crucial point, then there is an opinion on the attack which is performed by the attacker. So this is the probability of the attack taken by this guy. Also there is a loss function, and here we have a very simple loss function we see in the next slide, in which we have LD of d theta. We have decision space is very easy, d naught, d1. D naught means the defender chooses theta naught as the true value of the parameter. D1 chooses theta 1. It's very, very easy. So this is the loss function. So the decision by the defenders is d naught or d1, and the actual value of the parameter is theta naught or theta 1. Of course, if the defender chooses d naught, which means theta naught is true, and theta naught is true, there is no loss. The same if she chooses 1 and 1 is true, there is no loss. The worst case is the case in which d naught is chosen, so she says theta naught is true, but is not true. And then there is this value CD that we assume is less or equal than 1. We could have swapped the two of this, but we assume in this way. So this is a very simple loss function. And now the goal is try to find the actions which minimizes the expected loss. So the expected loss, this is the loss function for different choices of the parameter theta, and this is the probability of the parameter theta given the observed Y. In this case, we are supposing that the defender knows everything. So knows all the probabilities I wrote before are known by the defender, and in this case, this probability can be obtained obviously as the ratio of the joint distribution density by the marginal one. Well, you should trust me, this is the formula. And then we compare, in this case, we get rid of the denominator because it's the same under theta 1 and theta naught. So this is the condition. So the support for theta naught is the optimal decision for D if and only if this condition is fulfilled. Mathematics is easy in this case. We don't go through that. Now, the problem is that the expert has no idea about, the defender has no idea about the action of the attacker. So the crucial point is to find something about the distribution of the action by the attacker. This is the crucial point. So the idea here is to go to the attacker point of view and look at the point of view, at the problem from the attacker point of view. Now you can see, as before, the only difference is that now A is a decision and D is random, because the attacker has to make a decision, but he doesn't know what the defender is going to decide. So this is what we are doing. From a point of view of the attacker, the issue is equivalent to the point of view of the defender, more or less. Again, there are two hypotheses, and the attacker has some opinion on them. There are beliefs on how the data depend on the hypothesis. There are also beliefs on the consequences of his actions on A when modifying X into Y. So this is the consequences, because of course the attacker modifies from X to Y, but he doesn't know exactly what is going to happen in terms of consequences. And also the attacker has to have some opinion on the decision of the defender when the attacker is choosing Y, which is this one. There is a loss function in this case, and the loss function is something like this, like before. Again, the highest loss function is when theta naught is the true value of the parameter and the defender is choosing theta naught. This is the worst for the attacker, of course. It was the best for the defender, but of course is the worst for the attacker. And there are these conditions. So, and also the case we are considering is this one, so this is one, so this is really the worst it could happen. This is the best from the point of view of the attacker, because if the defender says theta naught, but the true value is theta 1, this is the best for the attacker, and these are the other two conditions which are subject to these conditions. Now, we are the defender and we are trying to solve the attacker problem. What is the problem of the attacker? Well, he has to find the actions, the best action from his point of view. So it has to minimize the expected loss from his point of view. Here you can see overall possible decisions, overall possible values of the parameters, integrated with respect to all possible observed actual X and all possible Ys. So, and then the choice is to choose the A, which minimizes this quantity. So this is easy, written in this way, but there is an issue. The defender knows nothing about all the probabilities given by the attacker. This is the major difference with previous approaches in game theory. We have to make some decision, some inference, some assessment about the attacker's probability. And the idea here, the one we are working on, is that all the probabilities and utilities of the attackers are coming from some random process. So there is a random process which gives us all the probability. There is a random process which gives us the loss of the attacker. This is the way in which we are modeling. This is the novelty of the approach which is related to adversarial risk analysis. So instead of having a prior for the belief of the attacker expressed through a prior, we have a process on the top of that. From that we are generating priors and simulating by generating priors from this process. And the idea is to find, through this simulation, to find values of A, which is the optimal random attack. When I use capital letters, these are random variables or processes, not realizations. So we have to find at the end of the day the probability we were interested in. This is the one which the defender does not know. This is the one which is very, very important. So what is the attacker going to do? What will be the decision of the attacker? And we will be able to find this A star equal to A that will be sorted, we will be able to find. So the idea is the following. So we have these random processes about priors, random processes about utility, and we generate distribution. We generate utilities, and for each generation of priors and utilities, we compute a value which is the optimal one. We keep repeating this one. At the end of the day, we will get plenty of this A sub K star. So we keep generating from these processes priors, utilities, keep computing at each step one optimal actions. At the end of the day, we will see what is the distribution, the empirical distribution of this A. So we will approximate the probability of an action A as just as a frequency of the times in which A star K was equal to A, divided, of course, by K, which is the sample size. So this is the idea. And the point is how to do it. Well, for example, what we have been working is something like this. How to build the distribution on the hypothesis. Well, for us was just probability of theta naught, theta 1, but it could be theta naught, theta 1, theta 2, theta k, many of them. So the idea is to build a Dirichlet distribution. A Dirichlet distribution from which generate the probability for the attacker that it will be theta naught or theta 1. But which Dirichlet distribution? The idea is to look at the mean of the Dirichlet distribution and center the mean of the Dirichlet distribution from which we are generating distribution for the attacker. So putting the mean equal to the distribution of a defender. So the mean of the process generating priors for the attacker is actually the prior for the defender. This is the idea. So we are perturbating the prior of the defender in some way by using the Dirichlet distribution, or if it's a continuous one, a Dirichlet process. And we put also some uncertainty on the others, and also we use a parametric form on the loss function. So we are generating. So this is the idea. So we generate this distribution. As I said before, we keep going back and forth from the defender to attacker and so on, but at some point we have to stop. And when we decide to stop, we will put some non-informative distribution, which will stop this process. So the defender in this point, this is the problem which the defender has to solve, as I said before, minimizing the expected loss, which is equivalent to this one. And the idea is, from the point of view of the attacker, is that the attacker does not know about this one. So again, the attacker has to put, as I said, distribution on this one. So there is a lot of random distributions, random processes from which we are generating the distribution. So the example, the very simple example we looked at is the following. We have data coming from an exponential distribution of parameter theta sub I, and theta sub I can take two possible values, 2 and 1. Theta naught is 2 and theta 1 is 1. And the decisions are very simple. The defender has to choose one of the two. D naught chooses theta naught, D1 chooses theta 1. We start giving priors to all of this, and the priors over the hypothesis is 1/2 each one of the two hypotheses. And then there is an action taken by the attacker. This is, as I said, a very simple model, but just to give an idea. So the attacker, when the attacker receives X from this exponential model, has three possible actions. Keep X, double X, so here you can see it can go Y equal to 2X, or can halve it, so divide X by 2. So these are the three possible actions. And the probability, in this case, we suppose the defender, is knowing the probability are this one. So the probability of the first attack is 1/2, 1/6, and 1/3. So we can solve this problem. There is a loss function, the one I already presented before, but in this case, this is the matrix that we get. This is 3/4. And we do the computation. The computation essentially is accept the option, the hypothesis theta naught equal to 2, if the Y that the defender is receiving is less than this one. So this is essentially solving our problem when we suppose the distribution of the actions for the attacker. There is this assumption. So the defender knows in which probability the actions are chosen by the attacker. And if we change a little bit the probabilities of the hypothesis, this is a way of saving our initial wrong computation. So we did this with 1/3 and 2/3, and we found out that in this case, D1 is always the optimal action. Since we didn't want to throw it away, I put it as an interesting case in which just changing a little bit the probabilities, the optimal action is always this one, D1. So saying that theta is equal to 1. So now what we did was the following. As I said, the assumptions we made was very strong. So the defender knew the probability with which the attacker was choosing the actions. We don't know that. So what we are doing here is generating, as I said before, attackers, probabilities, and utilities from some random process. How do we generate them? Well, the probability of θ1 is drawn uniformly on some interval. The probability of the data, given θ, comes from a gamma distribution with mean equal to the true values of the parameter and variance which is chosen uniformly. This is giving the randomness in the choice of the prior. We put a direct distribution here, and then we can compute the probability of a decision of the defender given y. So now we are from a point of view of the attacker. What is the probability for the attacker? The decision by the defender will be d, given that y is given. I will skip all the computations because I know they have already been quite very boring, but there are computations here, trust me, so we are able to do this, and then we generate also the loss function in this way. So loss function is this table, but then how do we generate the values which are missing here? We decided for simplicity to fix this one at 0, and this one is uniformly drawn. So this is a way of a very simple way of generating a loss function from a process. It's a very, very simple way. We could think of something more sophisticated, but this is very, very simple. And then here we have the random expected loss, because they are generated from this random process. These are the random expected loss for the attacker when choosing A0, A1, and A minus 1, which is the other action. So we keep repeating, we are generating, estimating this probability. As I said before, at the end of the day, we were able to estimate the probability of this one, and then as a consequence of that, putting all these results in the machinery, complex machinery I somehow skipped, is that the optimal action in this case is to choose θ equal θ0, which is 2, when y is less than this value, which is different from the previous solution, the case in which we knew the distribution. Okay, this is the algorithm, just forget about it. And then just to see an example, since I have still more or less 15 minutes and only 28 slides to go. Batch acceptance model. So the idea here is there are a batch of items which are received over a period of time, and some of them might be faulty. The point of view of the defender is to accept the batch or not. The point of view of the attacker is to let the defender accept in the batch when the batch is faulty. So that is what he is trying to do, to convince the defender to accept a faulty batch. And therefore, there should be some loss from the point of view of the defender. So we have a batch with two possible types of items, acceptable or faulty, and the decision by the defender is to accept or reject the batch. The data are coming according, the batch size is modeled by using a Poisson distribution over unit type, which means homogeneous Poisson process with parameter lambda. And also we suppose that there was some previous experience by this person, so that she has some opinion on the parameter lambda, which is a gamma. This is a gamma distribution obtained from a prior distribution observing something in the past, and this is the posterior. And this lambda is important or not, it depends. If the defender knows m, the batch size, it's not important how it was generated, how m was generated, therefore lambda is not important. Lambda is important in generating the size of the batch. If we know that, we don't care about lambda. And here we have the item which is acceptable with probability θ, and as I said the other day during my mini course, what is this? So if there is a batch coming of items according to a homogeneous Poisson process of parameter lambda, and with probability θ they are acceptable, and 1 minus θ they are not acceptable, what are the processes that we are getting here? Again, homogeneous Poisson process with parameter lambda θ and lambda 1 minus θ. So it's possible to do the computations, and So we have also some distribution. So the total number of items is Poisson. The total numbers of acceptable items is Poisson with parameter lambda or theta. And if we know M, the total number of acceptable items follows a binomial distribution. So this is our problem, the decision from the point of view of the defender without adversaries. So we have a decision which has to be made and a loss. Here are the data which are coming. This is M, which is affecting the sample size, which is affected by the value of lambda, and theta is affecting the acceptable one. So these are the acceptables, which are a consequence of the probability of being acceptable and the sample size, and that all of them have effect on lambda. So here, the idea in this very simple example is the defender is accepting the batch only if so it's good for the defender if all the items are acceptable. If at least one is not acceptable, that is bad for the point of view of the defender. So from a point of view of probability of having all of them acceptable, given that M is the sample size, is theta to the M. And this is the other probability that sum is faulty. So the expected loss over all possible x's is this one, if you accept D naught, and if you reject, is this one. So we can compute the expected loss. At the end of the day, we are able to come up with a rules, which is this one. So in this case, we are supposing that M is known. So if M is known, this is the accept the batch if and only if this condition is fulfilled. But if M is increasing, we see that this quantity is decreasing. Therefore, there is a threshold value such that there is a rejection of the batch when M is exceeding this one. Well, for the case we are considering beta, this is the quantity, so it's possible to compute M sub A. If M is unknown, well, you have to do some computation, and you come up with something like this formula. Probably most of you have never seen a book called Gradstein and Rizek. I guess Nikolai is able to pronounce better this. It's a book which is of this thickness and is completely full of integrals of special function series and so on. It's the most used book in my institute. It's completely destroyed. So, because going back to the old days when we had no computers with Google, everything you wanted to know, we used a lot this book to find integrals. And there you can find the hypergeometric function like this one. And then there are other possibilities. So you can think of each fault is counting, and then it is a different loss function, but I will not go through it because it's just. And then there are different, so now that was the problem from the point of view of the defender, with no attacker. Now there is the attacker. What is the attacker doing? The attacker is modifying the data. How is the attacker modifying the data? Well, there is a batch of size M, and M is known by the attacker. So the batch size arrives to the attacker. The attacker may do something. And here we will see after that three strategies will modify the batch size, and then it will communicate to the defender, and the defender will have to make a decision if to accept or not the batch. So this is another by agent influence diagram, is essentially like before. So now we have three possible strategies. Well, strategy number one is the following. The attacker receives M items, which may be M messages, and adds his own Y1, adds some other one, which are faulty. So that the defender is getting M, the original one, plus Y1, which are faulty, added by the attacker. Second possibility, M are received by the attacker, and the attacker is changing some of them, making some of them faulty. Third possibility, combining the previous two, adding faulty and changing some of the actual ones. I'm going to skip all the details. Well, you can find probably the slides in somewhere on the website, but it's or the paper when it will be ready. There are a lot of computations here that I'm going to skip. So, because I just wanted to send a message of this, because I don't want to show you all of this. So there are a lot of issues here. Now, okay, this is the formula, okay, but I'm not going to discuss it. The point I was making was I already made it. Now, this is again the random stuff, and this is the way again of generating. As you can see, this is just more complex with respect to the simplest model, simple example I presented to you earlier, but then we have other strategies and so on. Let's forget about this one. Now, last 3 slides in last 5 minutes. This new adversarial risk analysis is a new approach to dealing with this adversarial hypothesis testing. As I said before, symmetric losses and strong common knowledge assumptions are not very realistic. What are the directions that we are going to work on? Of course, applications, that's something, but also the idea of having more defenders, more attackers. And the attackers could cooperate among them, could not cooperate among them. The defenders could cooperate or might observe just part of the data. Also, the attacker could add good messages, not faulty, acceptable items, could make confusion adding this one. So there are a lot of possible applications. The one we were mentioning here is about adversarial signal processing. For example, in electronic warfare, there are these signals which are sent, there are many radars sending messages, and some other could try to jam this signal. So this is something which has some relevance. It's just to conclude about a couple of works. This has already been published. The other one is still in progress, but almost done. So this one is about robustness. As I said at the very beginning, I've been interested in robustness, which means considering instead of just one prior, instead of just one utility function or loss function, considering classes of prior, classes of losses, and see how the decisions corresponding to them are changing when we are changing priors and losses. Here we are going the same. As I said before, we are generating from some random processes, we are generating priors, we are generating losses. But that was a Dirichlet process, for example. But the idea is to consider classes of Dirichlet process for which we are generating. So there is another robustness issue. And the very last slide is this one. There was some work by Lindley and Singh-Purvalla in 1991 about acceptance sampling, and it was done in a game theory environment. What we are going to do is in adversarial risk environment. So suppose there is a manufacturer that I will call she, as before, which is trying to sell a batch of items to a consumer C, he, who might accept or reject the batch provided by M. The point is that the decision by the customer depends on the fact that the manufacturer is providing a batch of items to him, so some evidence. So the manufacturer should send a sample from its production of his items. And from the point of view of the consumers is to accept or reject the product, but from the point of view of the manufacturer is, should she send a batch of items to the consumer, and if she does, what should be the size of this one? So we have an issue which is somehow related to the reliability of the item, for example. And what we are going to do here is a sort of Bernoulli acceptance sampling. So we have something which may be acceptable, not acceptable. So this is the example we have been working. Also, we are interested in a life testing problem, which is essentially sending something which is might last a lot or not. So something related to reliability. So just to conclude, yes, just to conclude, I would say I know that it was quite difficult to follow what I was doing, but the idea here, as I said, is a very simple problem, hypothesis testing. When someone is trying to modify the observed data, is acting against us and wants us to make a wrong decision. The point is that we don't know what the attacker is exactly doing, thinking. We have just to guess about that. And this is a way of modeling what this attacker, what he's doing, and this is a sort of area I think is quite important, because especially if there is an area of huge interest for statisticians, which is risk analysis. Risk analysis is very, very important. It goes from, as I said, counterterrorism, bioengineering, and so on and so on. And it's really, really important to understand what other people, which might be people or nature or what else, are doing to make the best decision. Thanks a lot.
Question, perguntas? We have time.
Thank you for a very nice talk. It's an interesting matter. I didn't know anything about that, but I was wondering about how the dimensionality of this approach affects, for example, if you have a lot of variables to access and incorporate in the model, how to get rid of this dimensionality and the importance of, for example, prior elicitations, and how to deal with, for example, in the companies' competition or terrorism issues and so on.
No, your point is a very good point. I mean, that it's already complex. As I said, this is a simple example, but you have seen that it was not so simple, actually, with just two variables. So, no, it will be a huge problem. But the Bayesian non-parametric approach, the way of generating from a Dirichlet process, generating from these random processes, is some way of getting rid a little bit of the parametric assumption. So I am a strong supporter of the choice of proper priors and so on, but this non-parametric approach allows you more flexibility. That's one of the reasons for which, one of the many reasons for which Bayesian non-parametrics nowadays is so important. And that is what we were trying to generate, I would say. Priors out of processes, utilities out of process. They were a simple example. I mentioned the Dirichlet process. I think that is the direction, but it's computationally very, very complex. I fully agree. We will explore it in the next few years.
One more quickly question. Uma questão rápida, alguém? Então vamos agradecer novamente.
Okay, thank you.
Palestrante.